Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture Lecture Series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. The fastest supercomputer costs the budget of a small nation. It is purchased because the fastest supercomputer gives meaning to life, and because the fastest supercomputer makes the world a better place, and because the fastest supercomputer makes humanity more knowledgeable, and because the fastest supercomputer of today will become the computer of tomorrow. A faster supercomputer proves that humanity is progressing in the right direction. A faster supercomputer increases our level of civilization and enables our children to do better than us. The supercomputer that computes in parallel is the most important instrument in excruciatingly detailed computational physics and in extreme scale computational mathematics. In the history of mathematics, the answers to the biggest questions don't come easy. The solutions to the biggest questions demand big ideas and hard work. To the leaders of thought in the world of mathematics, the biggest question in calculus is this: how can the 21st century computational mathematician harness a new internet that is a global network of millions or even billions of processors, or harness a global network of as many tiny computers, and harness that new internet to solve a system of coupled, nonlinear, and time-dependent partial differential equations of calculus. My 1989 solution of the toughest problem in calculus was the front page story of the top mathematics news journal, namely the May 1990 issue of the Siam News that was published by the Society for Industrial and Applied Mathematics. To the world leader debating how to mitigate the consequences of climate change, the toughest problem in mathematics is this: how can the supercomputer scientist solve an initial boundary value problem, such as executing a general circulation model and executing it to foresee otherwise unforeseeable global warming? Solving the toughest problem in calculus demands the most powerful processor or supercomputer ever built or imagined. Yet, the toughest problem in calculus cannot be solved with only one isolated processor that was not a member of an ensemble of processors, or only one isolated computer that was not a member of an ensemble of computers. The computer is not powerful enough to be used to solve the toughest problems in calculus. Only the fastest supercomputer can be used to solve the toughest problems in calculus. It took me 20 years to learn and discover how to solve the toughest problem in calculus. During those 20 years onward of June 1970, I studied physics, mathematics, and computing. I studied to be a triple threat and to possess the interdisciplinary knowledge and to be a polymath that possessed knowledge that is beyond mathematics. Only a polymath can experimentally discover how and why parallel processing makes computers faster and makes supercomputers fastest. That experimental discovery of massively parallel processing that was ridiculed as a waste of time required that I be a polymath that is simultaneously at the frontiers of knowledge in algebra, calculus, physics, computing, and in particular, master how to communicate my codes and how to send and receive those codes, and how to do so across a new internet that is a global network of 65,536 equidistant processors. That parallel processing problem of supercomputing was called a grand challenge for a good reason. It's true that parallel programming, the precursor to the modern supercomputer, and parallel programming, that massively parallel supercomputer, to compute in parallel or to process many things or processes at once is no walk in the park. The technology of parallel processing was so terrifying to the vector processing supercomputer scientists that the June 14, 1976 issue of the Computer World carried an article titled, quote, "Research in Parallel Processing Questioned as Waste of Time," unquote. I had the confidence to make the impossible to compute possible to compute and make it possible at the crossroad of physics, calculus, and computing. I had the confidence because I was trained for 20 years and trained in physics, calculus, algebra, and computing. I had that confidence because I had received positive feedbacks from computational mathematicians. I had that confidence because I had given out-of-town research seminars in supercomputing in 1982, 83, and 84, and seen the reactions of the scientific community, I had that confidence because I had seen the looks on their faces when I explained to supercomputer scientists how far I had progressed in my then ongoing research in massively parallel processing. Another reason for my confidence was that in the 1980s, I attended 500 weekly research seminars. Each seminar speaker was invited because he discovered a method in computational physics or contributed an equation to calculus or invented a technique for solving a large-scale system of equations of algebra and solving them on a supercomputer. I had that confidence because I knew firsthand that I, Philip Emeagwali, was more knowledgeable than those 500 research scientists. I had that confidence because I became a polymath after 20 years of training and competing against 25,000 computational mathematicians that each had only 10 years of training and that each only had programming experience with vector processing supercomputers. Metaphorically speaking, I had the confidence of a 20-year-old male professional wrestler that was challenged to a wrestling match against a 10-year-old female professional wrestler. I was the 20-year-old boy amongst 10-year-old girls. For those 25,000 computational mathematicians, parallel processing was a pipe dream. For I, the lone wolf at the farthest frontier of massively parallel processing, it wasn't a pipe dream. During my scientific quest to experimentally discover how and why parallel processing makes the impossible to compute possible to compute, I was alone and at the crossroad of calculus and computing, and at the crossroad of physics and supercomputing, and at the crossroad of algebra and parallel computing. After the first decade, and from the frontiers of knowledge of the partial differential equations of calculus, I saw the horizon of the uncharted territory of massively parallel supercomputing. That technological vision gave me the motivation to spend my second decade in narrowing my focus to how to experimentally discover massively parallel processing. In 1989, it made the news headlines that I had experimentally discovered how to solve the toughest problems in computational physics and mathematically discovered how to compute their answers across a new internet that I visualized as a global network of 64 binary thousand processors that are equal distances afar and apart from each other. I visualized those 2 to the power 16 processors to be on the 15-dimensional surface of a globe in a 16-dimensional universe. I visualized 16 times 2 to the power 16, or 1,048,576 bidirectional email wires that are uniform and regular. I visualized those 2 to the power 20 email wires that were on the surface of a globe in 16-dimensional hyperspace. I visualized those 1 binary million email wires as the means to circulating emails that nourished my 64 binary thousand processors. I visualized those 2 to the power 16 processors as nourished with arithmetical data that I needed to solve my large-scale initial boundary value problems of computational physics and calculus. I visualized my boundary data and the intermediate answers to my initial boundary value problem as flowing via emails to and from 16-bit long email addresses and to and from each and every of my 2 to the power 16 processors. I visualized my arithmetical data as transmitted via emails to and from along 16 directions that were, metaphorically speaking, mutually orthogonal. That is, 16 directions that are mutually perpendicular in an imaginary 16-dimensional universe. I visualized my emails around my calculations on the surface of the globe in hyperspace. I experimentally discovered how to unravel my email pathways that went to and from metaphorically equidistant processors that I visualized as on the surface of a globe in hyperspace. I visualized how to map those 64 binary thousand points onto the surface of a globe in our everyday space, such as planet Earth. I visualized my global network of processors as having applications towards global circulation models. I experimentally discovered parallel processing by narrowing my focus to the hypersurface of that hyperball in hyperspace and by throwing away the less promising nitty-gritty engineering subject matters and throwing unnecessary details over the side. For the decade of the 1980s, I sat alone, staring at an abandoned, massively parallel supercomputer that everybody else ridiculed as a huge waste of everybody's time. There was no instruction manual on how to harness the power of the then never before seen massively parallel supercomputer that was abandoned for me to parallel program alone. Nor was there a help desk that could explain how I could synchronously send and receive 64 binary thousand emails. Back on June 20, 1974, when I began to program sequential processing supercomputers, there were an average of 24 programmers logged into the sequential processing supercomputer that I was programming. Those were the good old days when it was possible to program the world's fastest supercomputer and do so alone. On June 20, 1974, I even had a supercomputer instructor, had a supercomputer instruction manual, and a supercomputer help desk. But a decade and a half onward of June 20, 1974, I was the lone wolf programmer that was at the farthest frontier, that was the most massively parallel supercomputer ever built. In the 1980s, I had no massively parallel supercomputer instructor. The reason was that parallel processing was then considered a waste of time. In the 1980s, I had no massively parallel supercomputer instruction manual. The reason was that parallel processing was at that time not yet experimentally confirmed. In the 1980s, I had no massively parallel supercomputer help desk. The reason was that in that decade, no supercomputer scientist could answer questions on how to parallel process and harness the total computing power of a global network of 65,536 processors. That massively parallel supercomputer was the precursor to the modern supercomputer. In the 1970s and 80s, I was ridiculed and laughed at for attempting what seemed impossible to compute, namely, to program massively parallel supercomputers and program them to solve the toughest problems in computational physics and parallel program such supercomputers powered by up to 65,536 processors alone. For that experimental supercomputer of the 1980s, only one person can control its 65,536 equidistant processors. Only one person can lock all its processors and lock them simultaneously. I, Philip Emeagwali, was the lone wolf that was at the farthest frontier of massively parallel processing and the supercomputer scientist that controlled all those 65,536 processors and controlled them at all times. I experimentally programmed a room-size model or a working prototype of the modern supercomputer that could be constructively reduced to the planetary-sized internet. I said that I, Philip Emeagwali, working alone, invented a supercomputer that encircled a room-sized globe that I visualized as an idealized model of the internet that encircled the earth. I also said that although the supercomputer had 25,000 vector processing supercomputer programmers and had many fathers and mothers and uncles and aunts, that I am the only father of the supercomputer that invented a new parallel processing supercomputer and invented it as the lone wolf at the farthest frontier of the most massively parallel supercomputer. Because the modern supercomputer is now automated, making it easier to parallel program, it seems every other person could be a supercomputer programmer. Unlike in the 1980s, there is no lone wolf massively parallel supercomputer programmer. Consider the quantum computer. In May 2016, IBM Corporation made its 5-qubit quantum computer available to the public. That 5-qubit quantum computer attracted 40,000 users and attracted 275,000 quantum computer experiments. 30 years earlier, or in the 1980s, Philip Emeagwali, was the lone wolf programmer and the only person that was attracted to the most massively parallel processing supercomputer ever built. In the 1980s, none of the 25,000 programmers of vector processing supercomputers could harness even 8 of the processors of a massively parallel supercomputer. Nobody except I that devoted 16 years to the parallel processing craft will touch the technology and do so with a 10-foot pole. You may ask, why do we have 40,000 early adopters for the first quantum computer, but only had one early adopter for the first massively parallel supercomputer? The reason is that in the 1980s, it was 40,000 times more difficult to parallel program across a new internet that is a global network of 65,536 processors than it is to program one quantum computer of today. Recently, a 12-year-old that was writing a school report on the invention of the parallel processing supercomputer asked, why is Philip Emeagwali called the father of the modern supercomputer that computes in parallel? I answered, I am called the father of the parallel processing supercomputer because for 16 years I was the lone wolf in a pack of 25,000 supercomputer scientists in the world that stood alone and at the farthest frontier of supercomputing called massively parallel processing. I was the first supercomputer scientist to be widely recognized for his experimental discovery of how to compute many things at once instead of computing only one thing at a time. The reason the 7th grader is doing a school report on Philip Emeagwali as the father of parallel processing supercomputers is that I experimentally discovered how and why massively parallel processing makes the supercomputer faster. Today, massively parallel processing is the technology that powers the modern computer, as well as the fastest supercomputer. I experimentally discovered how and why massively parallel processing across 64 binary thousand processors of a supercomputer can be faster than sequential or vector processing on one supercomputer, computing with only one isolated processor that was not a member of an ensemble of processors. It is faster by a factor of 64 binary thousand. My experimental discovery of massively parallel processing was extended by Chinese supercomputer designers and extended from my factor of 64 binary thousand increase in speed to their factor of 10,649,600 increase in speed. In the 1980s, my experimental discovery of massively parallel processing was science fiction to authors of textbooks in supercomputing. During the 1980s, the 25,000 supercomputer geeks that used conventional vector supercomputers to solve their most computation-intensive scientific problems were like a roll call of the who's who's across all disciplines of science, technology, engineering, and mathematics. It's often said that supercomputing is an interdisciplinary field. The largest supercomputer manufacturer in the United States or Japan or China is de facto an interdisciplinary research and development team. The fastest supercomputer in the world is custom manufactured by an engineering team of about 1,000 engineers and scientists. The largest supercomputer development project can have $1 billion budget. I envisioned a future for humanity that's powered by massively parallel processing. That technology is 180 degrees apart from sequential processing. Briefly, the heart of the computer resides on the processor, while the heart of the supercomputer resides and spreads across millions upon millions of processors. So comparing the computer to the supercomputer is like comparing one wave to the ocean to the sea. I discovered that creating a new technology creates a need for a new narrative for the history of technology. The date, June 20, 1974, was the day I first logged into a conventional sequential processing supercomputer. The first supercomputer I programmed was marketed as the world's fastest computer when it was manufactured back in December 1965 and 2 years before the word supercomputer was coined. The reason it was called, quote unquote, the first supercomputer was that it was the first computer that could compute at the record speed of 1 million instructions per second. The first supercomputer that I programmed was inside the computer center at 1800 Southwest Campus Way, Corvallis, Oregon, United States. Only 24 programmers were time-sharing that supercomputer. All 24 supercomputer programmers were logged in from 24 teletypewriters that were scattered around the state of Oregon. In 1974, the number of computer programmers in the entire world was counted in the thousands. Today, the number of information scientists in India alone is counted in the millions. As a researcher in quest for the holy grail of the fastest computation, my central objective was to forge a path to the modern supercomputer that's powered by massively parallel processing technology. In the 1970s and 80s, the difference between I and the largest research groups was that they had to write theoretical papers on a sometimes theoretical supercomputer in order to get paid. They don't get paid for attempting to make the impossible to compute possible to compute. Because I was black and African, I wasn't getting paid, which meant that I was the only supercomputer scientist with the freedom to make the impossible to compute possible to compute. That unpaid lone wolf black supercomputer geek had the freedom to devote a decade to experimentally determine how to program a massively parallel supercomputer, while the teams of six-figure salaried white researchers were writing hypothetical papers about how, in theory, a massively parallel supercomputer would be a huge waste of their time. For 16 years, I programmed 16 massively parallel supercomputers, while theorists wrote papers and textbooks about a massively parallel supercomputer that they never programmed. Their theoretical papers pertaining to the impossible to compute gave rise to the saying that parallel processing is a beautiful theory that lacked experimental confirmation. To write a theoretical paper on parallel processing and write it without conducting a companion experiment on parallel processing is akin to a fifth grader writing a school report on the contribution of Philip Emeagwali to the supercomputer and writing that school report without reading a book on the life of Philip Emeagwali and writing that school report without knowing the definition of the word supercomputer. It's akin to a fifth grader writing a book report on a book he never read. In the 1970s and 80s, I was the lone programmer going in the opposite direction and paradigm from theorists of massively parallel supercomputing. In my opposite direction, I defocused on what the textbook said, namely that parallel processing will never work. A supercomputer expert from MIT in Cambridge, Massachusetts, warned in the June 14, 1976 issue of the Computer World magazine that the massively parallel supercomputer is large and clumsy and a waste of time. As the lone wolf, at the farthest frontier of supercomputing. It was intuitive that I focused on programming the unknown massively parallel supercomputer instead of the known vector supercomputer. In the 1970s and 80s, I didn't fit and couldn't work as part of a team in conventional vector processing supercomputing who believed that parallel processing is a huge waste of everybody's time. I was dismissed from vector processing supercomputing teams and forced to become a one-person parallel processing supercomputing team. I had to forge a never-before-taken technological path to enable me to reach the terra incognita, that is the unknown world of massively parallel supercomputing, and where I discovered the fastest computations across my new internet. That's a global network of 65,536 processors. I had to forge a unique supercomputer path into the history of computing. Prior to my experimental discovery, parallel processing was dismissed as a beautiful theory that lacked experimental confirmation. I experimentally discovered that a new internet that's outlined and defined by a global network of processors that communicates and computes in parallel could become a new supercomputer. In the 1970s and 80s, I witnessed my global network of the slowest 65,536 processors change. That new internet changed like the caterpillar that slowly transformed into its final form. That final form was my metaphor for a small internet. That new internet that I visualized in the 16th dimension was my shape-shifting magic sword. The discoverer saw the unseen and became the magician that wields the sword of truth. Like the caterpillar, I changed during the 16 years onward of June 20, 1974. At age 19, I was programming a supercomputer that computed only one thing at a time. For the 16 years onward of age 19, I was always in the shadows and always on the horizons. To invent means to originate or to create a product of the inventor's ingenuity. We cannot assign a precise date, birth date, and a place to any complex invention such as the modern computer that continuously evolved over the past 7 decades. We all agree that the computer was not invented by a super intelligent lizard from the moon. The speed of the modern computer increased gradually, but made a quantum increase of a factor of 64 binary thousand in 1989. That was the largest recorded speed up since the programmable computer was invented in 1946. That first computer was in Aberdeen Proving Ground at the outskirts of Baltimore, Maryland. That is my wife's hometown and my second hometown. My contributions to the development of the internet, that is a global network of 65,536 processors, made the news headlines as the experimental discovery of how and why parallel processing makes computers faster, as the experimental discovery of how and why parallel processing makes supercomputers fastest. It made the news headlines as the experimental discovery of the world's fastest supercomputer. That experimental discovery of a new supercomputer was recorded in the June 20, 1990 issue of the Wall Street Journal. So, I ask, what day was the internet, that is de facto a supercomputer, invented? To the historian of the internet, my date of conception was June 20, 1974, or the date I began my quest on a supercomputer that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. 3 weeks after I began that supercomputing quest, and at age 19, I was on the cover of an Oregonian newspaper that circulated only in the cities of Monmouth and Independence, Oregon. So 1974 was the year Philip Emeagwali began his quest for a new internet. To the student writing a school report on the contributions of Philip Emeagwali to the development of the supercomputer, the answer is 1989, or the year my experimental discovery of parallel processing made the news headlines. 1989 was the year Philip Emeagwali and his internet, that is a supercomputer de facto, came of age or blossomed. There is no single flow chart that describes how to invent the first internet and how to become the father of the internet. Moreover, an invention has 3 birth dates. The first birth date of an invention is its date of conception. The second birth date of an invention is its date of constructive reduction to practice. The third birth date of an invention is its date of physical reduction to practice. In the summer of 1974, I conceived a new internet. My new internet was shifted upstage, but I constantly shifted it towards the center stage. Over the following decade and a half, I invented that Philip Emeagwali internet as a global network of computers, and it made the news headlines when I experimentally discovered that new internet as a global network of 65,536 commodity off-the-shelf processors. In the late 1970s, I constructively reduced to practice a new internet that is a global network of computers that arose from a kernel that had a one-to-one correspondence between the vertices of the truncated icosahedron and the processors of that new internet. It also had a one-to-one correspondence between the edges of the truncated icosahedron and the regular short and equidistant email wires of that new internet. I discovered that more commodity off-the-shelf processors and regular short and equidistant email wires can be added by triangulation of the truncated icosahedron. As the sole inventor of the Philip Emeagwali supercomputer, I had to know a priori the topology or the locations of my ensemble of processors and know where each and every processor or electronic brain is located, and know those locations both forward and backward, and know them with the completeness an American airline pilot had to know the geography of Nigeria to understand where Abuja is located. I visualized short email wires for processor-to-processor communications comprised of wires printed onto circuit boards. I visualized long email wires comprised of fiber optic cables and electrical cables. I visualized my ensemble of processors as communicating and computing together as one seamless, cohesive supercomputer. I visualized using plentiful, powerful, and inexpensive commodity or large numbers of available processors that were assigned for everyday computers as opposed to a few custom vector processors that were designed for the fastest supercomputers. My primary quest was to challenge the established truth. That established truth of the 1980s and earlier was that the slowest processors cannot work together to solve the most computation-intensive problems in algebra or in large-scale computational physics. As the sole inventor of the Philip Emeagwali supercomputer, I had to know a priori the topology or the locations of my ensemble of processors and know where each and every processor or electronic brain is located and know those locations both forward and backward and know them with the completeness an airline pilot had to know the geography of Nigeria to fly from Lagos to Abuja. I visualized short email wires for processor-to-processor email communications that I visualized as comprised of wires printed onto circuit boards. I visualized long email wires comprised of fiber optic cables or electric cables. I visualized my ensemble of processors as communicating and computing together and doing both as one seamless, cohesive, parallel processing supercomputer that is the world's fastest computer. I visualized using commodity or large numbers of available processors that were designed for everyday computers, as opposed to using a few custom vector processors that were designed for the fastest supercomputers of the 1970s and 80s. My contribution to the development of the supercomputer is that I made the impossible possible when I encoded the laws of physics into the partial differential equations of calculus that I discretized into systems of equations of algebra that I coded and solved across a primordial internet that I invented as a global network of 65,536 processors. In supercomputing, to discover or invent is to show that the impossible to compute is in fact possible to compute. The genius is the ordinary person that found the extraordinary in the ordinary. I conduct scientific research to know what is discoverable and knowable, but which nobody knows. To witness a scientific discovery that has rich, fertile, and far-reaching consequences is like walking into a forest and witnessing a lot of leaves fall on your head. Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. Let's keep our conversation alive at emeagwali.com. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.